What about arithmetic operations on these representable numbers? We've already seen some examples. And what we have to do is we have to talk a little bit about rounding. So what do we mean by rounding in this sense? I mean mapping a real number, the square root of 7, or maybe just a 7-digit number, to the closest representable number. That's what we mean by rounding. So for example, the square root of 3 I've written there. It's an irrational number. It has a infinitely long convergent representation. And the closest representable number to that is clearly 1.73 times 10 to the 0, representable in this 3-digit number system that we're playing with. So that would be considered rounding that number. Let's introduce some notation. The notation is really just for today's lecture. Today's lecture we're going to learn some lessons, and they're going to carry through the course, but they're mostly going to be lessons, and we're going to remember them at every stage when we're doing computations. We're going to remember that the computer can only represent finite numbers of things, and there's gaps between the numbers it can represent. Those are the key things we want to learn. We're also going to learn about the scale, how big those gaps are, and what are the real ranges of numbers that can represent. But the details are, interestingly, this lecture, the details are not going to show up much more in the course. It's really just some of the implications. But there is some notation that, just to make the lecture today more clear, we'll introduce some notation, and you probably won't see it again, except on the test. So if G is a real number, let's let R of G, so R will denote rounding, that's what it's supposed to, that's what I've used R, represent the closest representable number to G. So if we do a couple examples, R of, that first number is a nice rational number. It's described in terms of millionths. It's exactly some millionths. But it has too many digits. So if we round, we can see that it becomes 2.37 times 10 to the negative 1. Rounding the square root of 2 gives 1.41 times 10 to the 0. And then lastly, there I've rounded one that already is representable. 98.6 is representable. So the round of that is itself the same number back, 9.86 times 10 to the first power. So the first two examples definitely incurred some error. G was not a representable number, and the rounding gave a representable number. The last example, G was a representable number. Now there is a case of a tie. And in that case, what you do is you choose the representative number with C. Remember, C was the last digit in our 3-digit model. And you make C even. And that's called rounding to evens. So for instance, in the first example, I have 0.2375. Now, should I round the 7 up to 8 or down to 7? Should I round the 5? And if by this rule, we'll round to even, so I'll make it go to 238. On this next one, I have 1245. Now, if I round the 5 up, I'll get 125, but that will not be even, so I'll round that one down to 124. And we'll see again in the computer that same rule, it's just a rule, is used whenever the exact number, lands exactly between two representable numbers. What about arithmetic operations? Now, computers don't just store numbers, so for the last couple slides, we've really just been looking at the numbers that are storable and what type of gaps there are between them, and maybe some rules for how you map symbols to what the number really means. But computers also compute on these representable numbers, and ultimately the results need to be representable because the computer needs to store the result in its memory, and its memory is going to be using some sort of finite number system. Now, if you think about it though, arithmetic operations, forget about this class. The arithmetic operations that we all know, they're defined on real numbers. And real numbers, of course, include all the representable numbers. Real numbers is this continuum of numbers. And any of these representable numbers that we've talked about are just particular real numbers, a very small subset. In this case, a 9,100 element subset of the real numbers. So if I could do the exact arithmetic, those are clearly defined on the representable numbers. I do an exact division on two representable numbers, and I end up with some real number. But as we've seen, the result may not be representable. So our requirement is, and this is a requirement on the CPU, is that arithmetic operations must work. You must be able to add, subtract, divide, multiply two representable numbers. And the result that the CPU produces must be the closest representable number to the exact answer. Okay. Again, I've already alluded to this, and we are going to have to think a little bit about how this is even possible. But it is possible with a little more work and a little more circuitry in the circuits that actually do the operation. They have to carry around a little more precision, and then they're able to always do this exact rounding, perfect rounding. So what we actually need to do to make this clear, we need to introduce a little notation. Again, it's mostly notation for today's lecture. But we do want to differentiate between the exact operation and then the operation that takes place on the computer. It can get a little clumsy, the notation, so sometimes we'll even do a shorthand when it should be clear from context of what we're talking about. So let's first talk about exact arithmetic. So let's think about real numbers, not representable numbers, but real numbers. And I've just chosen some letters and a font, X, Y, F, and G, and those are all real numbers. So that's an element of the reals. So arithmetic operations on real numbers always result in a real number. The only arithmetic operation that you can't do is divide by zero. Dividing by zero. So let's notate these just as usual. X plus Y, that's supposed to be F divided by G, and then finally X times F. All familiar things that we're completely and 100% comfortable with and have been for years. Now, because this lecture is delineating between exact arithmetic and finite precision arithmetic, sometimes we're going to have to be a little more we're going to have to add a little more clarity to what's written on the slides. So I might, if need be, I might write the word exact and then the operation and then the two arguments in this case. These are all binary operations. So for instance, the first thing, X plus Y, I might write the exact result of applying the plus operator to the arguments X plus Y, and then also divide and multiply. On the other hand, we're also interested in what the computer is doing with its representable numbers, which are not all the real numbers, and then its arithmetic processing unit, which can only process those numbers and has to yield another number that's representable. So for that we need to, so I've already alluded that we have to be able to compute, and the numbers have to be representable. So when we're trying to be totally clear, we're going to use op for the computer operation instead of exact on the left-hand side. So there I've written almost the same thing. I've used a different font. I've used the Courier font. So we're going to let op denote the representable result of adding two representable numbers, in this case F and G. So here I see op, then the operation, and then the two arguments. Now what I said on the previous slide is that however the machine works, and however the machine does this, however the circuitry was designed by the Intel or Advanced Micro Device or any other manufacturer's engineers, when this is requested of the computer, the result it produces, op, and then the operation, in this case a plus, and the two arguments, it must be the result of the exact operation rounded to the nearest representable representable number. So that's something we can always count on. And any one operation, the computer operation, which is on the left, op, will always be the round of the exact operation, even though the computer didn't do the exact operation. So this is a requirement of the computer hardware, specifically this arithmetic processing unit. Now, all our MATLAB expressions that we've been typing all along in the previous lectures, we don't go through such a clumsy notation, op plus fg. We simply write f plus g. And implicitly, since that expression is being carried out on the machine, it is the op operation. It is the plus operation as that machine can implement it.